All right, so today I want to talk about voltaic cells, which are basically batteries, and we'll also talk about standard cell EMFs. That's at least this file. That's what it will encompass. And so I've mentioned this before, but I kind of want to show you the mechanism behind it. When water flows down, we can have it flow down over a mill, right? And by it flowing down over a mill, it will spin the mill, and the mill can be used to do work. And so in this particular example, it is literally grinding wheat to produce flour, as you can see here. So just by the water flowing down in the waterfall, you can extract work out of it. Now, when you're doing this, okay, so it's an important thermodynamic concept. You're not changing the quality of the water. The water up here is the same as the water down here. Just here it has higher potential energy, and as it's falling, it's losing that energy and transferring that energy into work. So it's kind of to remind you what we did in thermodynamics. Okay, so I'm getting useful work out of something that would have just gone away as heat. So I can just kind of extract that for myself. Can I do the same idea as this with electron flow? So the answer to that is absolutely yes. So I can have electrons flowing. It would flow across some sort of an element that I care about. And after it flows, I don't really care what it looks like. It's just going to be stagnant water or stagnant electrons, whatever. As long as this potential energy was used to do something for me. So yeah, let's look at that. Here's an example of a Voltaic cell, which is the basic idea behind a battery. And I'm not going to go over the terminology quite yet, but you could see basically electrons flow along these arrows spontaneously, just like it would a waterfall. So a waterfall of electrons going down this way. And I put a light bulb here. So they just happen to go across the light bulb, light it up, and continue. So the quality of the electrons from here to here does not change, but I just use this waterfall of electrons to mill my wheat to produce flour. I did the same thing here, but I got light out of it. So it's the same idea. And so what I want to do right now is discuss what the elements of this particular diagram are, so you can sort of understand basic voltaic cells. And voltaic, the word volt. Oh, you've heard that before. It's the same person. It's named after the volt, the unit volt, and voltaic cell. This is also known as a galvanic cell, just so you're aware. Okay, so as I mentioned, it's a spontaneous redox reaction going from this area to this area, and as electrons flow, they flow from where the oxidation takes place to where the reduction takes place. Okay, that's the general flow from oxidation and into reduction. Okay, and that makes sense because reduction in the reduction area, that's where electrons are being taken in. So remember, Leo says GER, gain of electrons is reduction, meaning electrons are coming this way to the reduction side, and they're being gained by this. Loss of electron is oxidation. Oxidation takes place here. It's losing electrons. Makes sense. So it's losing electrons and is going to where they want to be taken in. Okay, once the oxidation stops, meaning I used up my entire zinc in this particular example, I have a dead battery. Okay. Let's look at the elements here in the specifics of this voltaic cell. So in this particular cell, I have zinc and copper. Okay, and if I'm looking at the half reactions for zinc and copper, I have the oxidation is the zinc, and the zinc goes to +2, and it's losing 2 electrons, and the copper is being reduced. It's taking in 2 electrons to become copper solid. So you can see basically here you're going to plate more copper as you're going along, and here the zinc is going to be used up and basically dissolve in solution. So this electrode is going to be eroded as this battery, as this cell is going along, and the mass of this rectangle is going to diminish. It's going to all dissolve. The mass of this guy is going to increase because it's going to be plated with more copper, because I'm producing more copper in the reduction side. Okay, so it's going to be taking in copper from the solution and depositing it here. That's what's going to happen. Okay, electrons always flow from where the oxidation takes place to where the reduction takes place, and oxidation takes place in what we call the anode. Okay, this is called an electrode. This and this. These two things are called the electrodes. Okay, the electrode where the oxidation takes place is known as the anode. The electrode where the reduction takes place is known as the cathode. And here's a mnemonic: red cat, reduction cathode, and ox, anode oxidation. There's other ones, just happen to be the one that is stuck with me. I swear to you guys, Leo says Gur and red cat and ox, I use it all the time whenever I think about this. I just double check myself. Okay, so feel no shame for using this. It's silly and it's cute. So go ahead and use it. You'll notice I have this other thing, this salt bridge. Okay, and what it is, we always have a salt bridge to connect the two areas of the cell. And basically, as I'm depositing copper, as you can see, if I didn't have the salt bridge, if I'm depositing copper, I'm going to lose positive charge here. It's going to become more negative in this solution. And this solution is going to become more and more positive, okay? And as we know, in nature, things don't like to be charged. So to neutralize it, we have this salt bridge. And it's going to be a gel of a bunch of electrons. And the electrons would just flow to neutralize this stuff. So here, obviously, since I'm making more positives, the negatives will come in. And since I'm taking away the positives, I have negatives. I have positives coming in to offset that, okay? So I'll say the positives will always go towards the cathode. So cations always go towards the cathode. And the anions, the negatives, will always go towards the anode. Okay? So that's how you would always see it. Okay? See, the negatives goes here, and the positive goes here. Okay? And that's basically it. So if I were to try to, I'm going to give you an example, and let's do that now. Let's look at an example of trying to describe a galvanic cell. Okay? So let's describe that. Describe the following galvanic cell. I just got this marker, and I love it. So hopefully it's legible for you. So it looks like a pen. It's wonderful. All right. So when silver and magnesium interact, okay, which will be reduced and which will be oxidized? Well, actually, we haven't covered this yet. Let's get back to this question in a minute because I want to go over this in a second. So I apologize. Let's continue talking for another minute, and we'll be able to answer that question. Okay. So we know what a voltaic cell looks like. Okay. There's this thing called the standard cell EMF. Okay, and it is denoted as E superscript O, and it is a number, and it quantifies how much work I'm going to get out of my oxidation going into reduction. Okay, so it's going to quantify basically the voltage that I can get here for this battery, how much I can actually get. Okay, all right, and it is known as EMF. For electromagnetic force, but it's not a force, it's actually a potential, and it's measured in volts. Okay, so it's like a potential energy, it's an electrical potential energy. And the higher the number, the more work I can get out of the electrons, okay? That's the whole idea. And when I'm talking about standard and this zero thing here, it applies at standard conditions, which means it's 1 atm and 298 K, and everything there is at 1 molar. Okay? And the standard reduction potential is given to you in table 20.1. This is why I want to do this first, because now you'll be able to tell me which one is getting reduced, which one is getting oxidized. This one is going to tabulate the reduction potential for a whole bunch of half reactions. And so if I have two elements and I want to know which one is getting reduced, which one is getting oxidized, I'm going to look at this table, this is a copy and paste of your table in the textbook. This tells me how likely stuff wants to reduce. Okay, the higher the voltage, the more likely it is to get reduced. Okay, so fluorine, out of all of these elements here, wants to be reduced the most. Lithium wants to be reduced the least. So if I have fluorine and lithium, and I want to know which one of these is getting reduced, which one is getting oxidized, this is going to get reduced, this is going to get oxidized, and so I would flip it to get the oxidation half reaction. Okay, so now I think we can do this particular example, and I will look at more examples here with you beyond just this description. All right, so again, I have silver and magnesium, and they're interacting, and I want to know which one is getting reduced and which one is getting oxidized, which I just showed you can easily do. Now, I want you to write the net reaction, which we've shown how to do before. And then also now, how would you set up a cell, a galvanic cell, or a voltaic cell? Okay, and basically I want to know which one is the cathode. Identify the cathode, identify the anode. Okay, and if I have a salt bridge of NaCl, right? What I want to know is Na goes towards where? Migrates towards where? Towards which electrode? And same thing with Cl minus. Okay, so basically the whole gamut. I want to know everything about this. Okay, so first of all, I have silver and magnesium. So I'll go consult this table, silver and magnesium. Great. If I'm looking at silver here as a standard potential of 0.80 right here. So I'm going to write that down. I have silver plus an electron. I'm going to omit the aqueous part. And it's going to form silver solid. And it has a standard potential of 0.80 volt, meaning at 25 degrees Celsius and 1 atm. And this being at 1 molar, the voltage is 0.80. That's the amount of extraction I can get out of this. Great. I'm looking at magnesium. Magnesium is going to be, well, not here. So I will give you magnesium. Magnesium right now, I'll give it to you. So in this particular example, it wouldn't be on this table. So I'll give you the magnesium. Magnesium is this. Magnesium plus 2 electrons gives me magnesium. And its potential is negative 2.37 volts. So, okay, so imagine that you were either given this, or you can read that from a table directly. All right. So based on this, whichever one is higher, okay, which one is a larger number, is going to be the one that wants to be reduced. Okay, so meaning that the forward is what's going to happen. Okay, so since 0.80 is greater than negative 2.37, this to me implies that silver plus this reaction is what's going to occur. So this is going to be the one that's going to be reduced. And it means that the reverse of this is what would occur with magnesium. So I would get this. Magnesium is going to go into magnesium plus 2 electrons this way, right? That's how we would do that, right? And so this would be my oxidation. That's what that would mean. Okay, so now I know which one is getting reduced, which one is getting oxidized. Now to write the net reaction, I need to multiply the reduction half reaction by 2 so that I can cancel out the electrons. I don't want the electrons there. So I will get 2Ag plus 2 electrons going to 2Ag. This is very similar to Hess's law, you know? Mg going into Mg plus 2 electrons. Now the electrons would cancel, and I can add them up, and I get 2Ag plus, I'm going to reintroduce the fact that these are aqueous, plus Mg solid, going into 2Ag solid plus Mg plus 2 aqueous. So now I know which one is which one is being reduced, which one is being oxidized. I already knew that. This one is getting oxidized, and this one is getting reduced. Perfect. So I know all of this. Wonderful. Now, to do the galvanic cell, to do that, it's fairly simple. It's just basically you can draw. Let me draw the most general thing, and then afterwards we will fill it out. So the most general thing, without having any elements in it, I'm going to draw just the most general cell possible, without the identity of anything being provided. Okay, I have this right here. Perfect. So that's my salt bridge here. And this is going to be an electrode. This is going to be an electrode. Okay. And here along this way, I'm going to say electrons flow. Electrons flow this way. Okay, so I'm going to just erase this so I have room to talk about stuff. So I have electrons going from this electrode to this electrode, meaning that since electrons go from here to here, this is going to be my anode. So again, I'm not denoting anything about this particular question yet. I have anode, I have cathode. So pretty safe bet you can do this. You can just write this. This is going to be my salt bridge. Okay, so whatever the salt bridge is, I know that the negative ion will go towards the anode, the positive ion will go towards the cathode. Okay, great. I also know from, so let me just write this down here again. Red cat and ox. All right, it's not really visible. Okay, so the reduction is where is the cathode, and the oxidation is at the anode. So we also said that we already said that the reduction is the silver, meaning here I'm going to put this, the reduction is at the cathode. This is going to be silver. Okay, and here is going to be the N-ox. Anode is where the oxidation takes place. So this is going to be magnesium. Okay, I have NaCl in this salt bridge, Na plus and Cl minus. Well, the minus with the minus goes towards the anode, we said, and the pluses will go towards the cathode. That's how that would work. Okay, anything else am I missing? I don't think so. I think that's it. So basically, I'm going to have here in this solution, basically, let me put this all in. In this solution, I'm going to have Mg plus 2, and in this solution, I'm going to have Ag plus. And as this goes along, this dissolves. It's going to go this way. Mg plus 2 comes off of this electrode, and Ag plus is going to go here and deposit and form silver for me, because I'm going to lose magnesium and form silver. Okay, and this will stop when magnesium completely dissolves and I have nothing else, and this just offsets the balance. So since I'm dissolving a bunch of plus 2s, I'm going to have the minus come in and offset, so that's neutral. Since I'm losing all these pluses will come in to offset that balance. Okay, and that's it. That's how you describe a voltaic cell.